Hello, folks. Welcome back to another broadcast from the bunker. Hope everybody's doing well on this beautiful day. Today's topic, we're talking about deposition. That's after you break the sediments down, you carry them someplace, and then you dump them off. The dumping off is deposition. That's today's hot topic. Our do now is the new batch questions, 8A, numbers 5 to 8. So spend a few minutes on those, and I'll meet you back here. Okay. I'll start out with number 5. A couple of moon questions, a little lunar action. All right, the diagram below shows the moon in 4 different positions, A, B, C, and D, as it orbits the Earth. That orbit is going to be a counterclockwise motion around the Earth when viewed from the North Pole perspective. How does the moon appear to an observer in New York when the moon is at position A? Well, here's A. So let's double back to what we know for sure. If this is the Earth and the total dark side is facing the Earth, that's your new moon, right? So the total lit side is the full moon, and we're going this way from new to full back to new. All right. Position A, it looks like it's one of those 50-50 things. But remember, when it's on the bottom, what we said in class, rotate your paper or rotate your iToy to the top. So if I put my person there, when he looks up, what does that person see? Well, if you do that, and you look up, the shadow should be on the left side, right? If your person is here, draw the little person. Here's your person, that's you. And when I look up, I see the shaded part on my left. Remember, when you're looking upside down, it's opposite. So the shadow is going to be on the left side. Well, that's got to be choice B. And if you're talking about phases, well, this is the new phase. That's got to be one of your quarters, right? So new, first quarter, full, third quarter, back to a new. So let's label that right away. This is our new. This is our full. This is our first quarter. And this is our third quarter. And we're going on choice B there. All right? All right. Let's keep going. Number 6. Number 6 says, what is the approximate length of time the moon takes to travel from position A to C? Well, A to C is from new to full, right? So that's about a week there. That's 2 weeks there, 3 weeks, 4 weeks, right? The whole thing is a month, a month. So if you're going half of that from A to C is about 2 weeks. So your best option would be 14 or 15 days. Okay. So number 7, this one a little interesting. You got to break out your ruler, and you're going to need a calculator. Okay. It's talking about eccentricity. It wants to know the eccentricity of this orbit. Well, first you got to measure with your ruler from the 2 focal points. Remember, the formula for eccentricity is in your reference tables. All right, so I'll click back to that. That would be all the way at the beginning. If you forgot your formulas, they're all right here. So eccentricity equals distance between foci divided by length of the major axis. Well, let's find those 2 pieces of information out. So take your ruler and measure from here to here, and then from here to here, right? You're going to divide. So if I do that from focal point to focal point, I'm getting about 6 centimeters. So 6 divided by, now I'm measuring from X to X. And I use my ruler on my screen, and I'm getting about 7.5. So 6 divided by 7.5. Pardon my handwriting again, I'm writing on a vertical screen. So I type into my calculator here. Say, all right, I do the top number first, numerator first. 6 divided by 7.5, and hopefully you're getting something that looks like that. Okay? If you can't see it, that's a 0.8. Now, there are no units. The units cancel, so the closest thing we got there is choice B at a 0.8. Now, there is no planet that's that elliptical. That is extremely elliptical. Most of the planets are slightly elliptical. And if you go back to your planetary chart, I'll show you what I'm talking about. That's toward the end of your reference tables. Right here. The list of eccentricity right there, 0.2, 0.0, yada, yada, yada. The most elliptical is a 0.206, and that's Mercury. So a 0.8 is way, way off the charts. Okay? All right, last one, number 8. It says the diagram below represents the Earth. So if Earth is this big, how would Mars be comparatively? Well, how do you do that? Well, you got to figure out how big Mars is. Go back to your planetary chart. Earth's diameter is right over here, right, diameter. Let's say it's about 12,000. Right, we'll just keep it simple. And Mars, find Mars is about 6,000 roughly, right? Well, 6 is a half of 12. So you're looking for a model that's about half the size of the Earth. And in doing so, which one is half the size of that? Well, hopefully you chose B, because Mars is about half the size of the Earth. Okay, does that kind of make sense, I hope? All right, well, you know the deal. If you have further questions, leave them down in the YouTube comment section below. And speaking of questions, one of our fellow students asked if I could clarify the igneous rock chart percentage thing. So let's address that real quick. Okay, quick recap on the igneous chart. The minerals down here are all spaced out based on percentages of what's in the rock. So let's, for example, you have an average granite. When I said average, I'm going to go to the middle of granite and go down, and this spacing would represent the amount of potassium. This spacing for quartz. And you would take a scrap piece of paper and roughly figure out what those percentages are. So let's go through one real quick. Please grab a piece of paper. All right, and you're going to take your piece of paper and you'll go straight down from granite, and you're going to have to make a couple of marks on your paper. So for the first one, for example, you're going to mark right where the 0 is. Then you're going to mark every time a new mineral line hits on that paper there. So please do that right now. All right, I'm going to try not to write on my screen here. So my corner is 0. Then I have here, 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 and here. And now I'm going to abbreviate. So this was my potassium feldspar, pot F. This was my quartz, Q. This is my plagioclase feldspar, plag. This is my biotite B, and down below amphibole A. And now you're simply going to slide over and get your percentages. So amphibole, well, that's about at the 10, so I'm going to write a 10. Then I'm going to slide down. B, my biotite, is about at 10 again. I write 10, and I slide down. Plagioclase, well, that's about a 20. So I write 20 and I slide it down. Quartz, well, 25, 30, that's about a 40. And I slide down. And the last one Potassium feldspar, roughly 20 or so. And I write it in. So now on my piece of paper, I should add up to 100, right? About 100%. So 40 plus 20 is 60, plus 20 is 80, plus 10 is 90, another 10 is 100. And that would be about 100% of the mineral composition in your average granite. Remember to go down from the center. And you could do that for any of these rocks, same method, just go to the center of the word and go straight down. If you got to use the right side of the chart, do so. If you got to use the left side of the chart, do so. But always start with your scrap piece of paper that looks something like this. All right? Hopefully that cleared up any questions on that. Again, any further questions, write them in the YouTube comment section below, or simply send me a question on Remind. All right, let's jump into the lesson here. Okay, today it's deposition. Well, let's say all these particles are floating in the water. Which ones will get to the bottom first? Which ones will settle the fastest? Well, take a second, think that through, and I'm going to hit a little animation here. And boom. Let's do that again. Boom, I drop a whole bunch in the water. Who got to the bottom first? Well, hopefully you could see the rounder ones did. Rounder particles have less resistance, right? They have the least amount of surface area. So as they're sinking down, they have the least amount of water resistance in this case. In air, it would be a similar thing. If there were no air at all, they would all drop at the same time, right? But that's not the case on Earth. So in water, right, the rounder thing will settle first. Also, if it's heavier or denser, it will also settle first. And we're going to take all that down now. Okay? So there are a couple of factors that affect deposition. First one, of course, we talked about was shape. I have them out of order here. But the rounded one got to the bottom first. Then there's size. And if it's, you know, with the expression, the bigger they are, the harder they fall. Well, same in this case. The bigger they are, the faster they're going to fall. And density we mentioned, right? If something is very dense, it's going to drop much, much faster. Okay? Get these all in your notes, folks. Quick little background reading. Make sure you read that through. Okay. Deposition is your official definition of it. Sediments are dropped from an erosional system as the velocity decreases. It's also called sedimentation. As the wind slows down, it'll drop, it'll deposit. As the rivers slow down, they will drop and deposit. First, you break them down into particles, then we erode or transport them, and today we're talking about the dumping, the deposition. Okay? So there it is. Particle size, right? The bigger they are, they settle first, takes less time. The bigger particles are cobbles, pebbles, and sand. You might ask, well, how am I going to remember those particle sizes? Well, if you go back to your reference tables, there is a chart of particle size. It's near the igneous chart. All the way up here. There it is. We'll zoom in on that. And there, oh. Okay, here are your sizes, right? So from biggest to smallest, the bigger ones being boulders, cobbles, pebbles, sand. Well, pebbles anyway, and smaller sand, silt, and clay. So you don't have to memorize them, but you do not have to where to look. Okay. And here we go. So the bigger ones settle first. That's your cobbles, pebbles, sand, silt, and clay. And of course, the smaller ones will settle last. They'll take more time to settle down. That's why you usually get murky-looking water. Even if it's slow-moving water, it tends to stay murky because all that silt and clay stays suspended in the water and makes it look dirty. All right, what does a graph of this look like? Well, the bigger the sediment is, it should take more or less time. Very good. If it's bigger sediment, it takes less time. Everybody with your hands, what does that look like? Hopefully you chose that classic inverse there, right? As the sediment gets bigger, it takes less time. Now, how does that compare to rate, right? Here's your rate graph. If the sediment gets bigger, if it took less time, I must have done it at a quicker rate. So it's an opposite looking graph, right? A direct relationship there. Okay. Then we jump into shape. How does shape affect things? Well, we just said the rounder ones, the spherical ones will settle first. The sphere is the shape with the least amount of surface area, so it has the least amount of resistance, and it will get to the bottom faster. Okay, flatter particles will take more time. You can see the simulation happening over there because, again, more resistance. Okay, what does a graph look like? The rounder you get, it should take less time. So if I'm getting rounder, I'm taking less time. Compare that to rate again. These are opposites, right? If I'm getting rounder, if I took less time, I must be doing it at a quicker rate. Okay? Make sure you're getting all your notes down here, folks. And then, of course, we get into density. Well, the denser it is, right, it certainly will get to the bottom faster. And that's what it says right there. Okay? The less dense will take more time to settle. And if you have clay and silt, those are very small, low-density particles. They could be suspended in water for months, even after it's almost stopped moving. So you literally have to filter it out or wait a long time. If you remember in our classroom, we have those settling tubes at the top of the board, and I had them sitting there for months, and it still looked a little murky inside of it. Well, that's what's going on. They are low-density, flat particles taking a long time to settle. What does a graph look like? The denser it is, the less time it's going to take. And again, if it took less time, then you must have a faster rate. All right? Okay. What about now if I compare time and rate together? This confuses a lot of students. Hopefully we'll clear this up. If you do something at a quicker rate, it's going to take you less time, right? If you run around the track faster, you're going to have a lower time. So a quicker rate means it must be less time. Okay, inverse relationship there. This is called graded bedding, where year after year you get this varying size in this vertical sorting. And that's because in the springtime you get more rain. So more rain means more water in the rivers. It goes faster, carries bigger things. But then as summertime comes, you get less rain. It gets hotter. The water evaporates and the rivers slow down and carry smaller things. But then next spring it starts all over again. It's called this graded bedding cycle. You want to do an exciting rafting trip, you go in the springtime. You're going to be a little chilly, but it's a great ride down the river. You go in the summertime, you're going to be bored out of your mind, right? Because you don't get those spring rains anymore. The river slows down, and you're going to be bored. All right, so you set up a bowl of water. You're going to drop all these things in at once. Who's going to make it to the bottom first? Take a second and jot in your answers. Hopefully you said getting down to the bottom first would be the biggest, densest, roundest, and of course that would be boulders. Who's next? Who's the next biggest in the list? If you got to go back to your reference tables to check the sizes, that's fine, but certainly cobbles would be next. Next coming down, right, who's the next in line? Well, that would be pebbles, which reminds me of a funny joke. These kids were going to school, and this one kid runs in the classroom late, and the teacher says, "Hey, why are you late?" He says, "I'm sorry, I was throwing pebbles in the lake." So, all right, sit down, you'll have detention after school. A couple minutes later, next kid comes in. The teacher says, "Well, why were you late?" And he says, "I'm sorry, I was throwing pebbles in the lake." The teacher says, "All right, you got detention as well." About 20 minutes later, this little kid comes walking in soaking wet. The teacher says, "Well, why are you late?" The kid says, "I'm pebbles." Get it? All right, keep going. The next in line, of course, sand will settle, followed by silt, and finally clay. And here we have, again, that vertical sorting. Down here you would make the sedimentary rock conglomerates. Here you would make your sandstones. Here you would make your siltstones. And up top you would make clay turns into shale. Good. All right, get your final notes down there. Small, flat, less dense at the top. Large, round, more dense at the bottom. All right, couple summary questions. A river flows from 100 to 50 centimeters per second. Take a few minutes and crank on these, obviously. Hit pause and then come on back. Well, if we go from 100, 100 was carrying all of this stuff. But if I slow to a 50, I'm going to drop some of those bigger pebbles. So hopefully you chose here, you're going to carry clay, silt, sand, and small pebbles, but the bigger pebbles will drop out. They'll become deposited. All right. Next up, which stream velocity carries only clay particles and eventually deposits them to form shale? Well, if you're just pushing clay, you are way slow. That is a slow old age river, right? The older rivers go slow. So you're looking at like 0.0 something. Hopefully you chose 0.02. All right. Keep going. And a sample here, the particles have the same shape, but they're different sizes. Well, the bigger they are, the faster they fall. What's going to make more sense when these particles deposit in a quiet body of water? Hopefully you chose this guy here. The bigger they are, the less time it takes to settle. On this side, with in a more vertical sorting, quartz particles of different sizes, so they're all the same mineral, they have the same density, but now they're different sizes, are dropped in at the same time. Which cross-section pattern will most likely you see? Well, you're going to find bigger on the bottom and smaller on the top. So the only one that makes sense is choice 3. Okay. All right. Any further questions, please leave them on the YouTube comment section. Remember, grades are being calculated very soon. Make sure your work gets submitted and submitted properly. Read this through many times. There's still some people not quite sure how to submit things. Please read this through very carefully. All right. And again, for additional questions, put them in the YouTube comment section below or text me at Remind. All right. Hope you get outside and enjoy some of that sunshine today, and I'll see you tomorrow.